Hi, my name is Dave, amateur radio call sign AB7E, and today I'm going to try and show you how you can 3D print your own boom to element brackets for maybe a Yagi antenna or something like that. I'm using an application called OpenSCAD to create the model. It's a free open source application that's remarkably easy to use. It uses functions and formulas to create the model, and you can see over here on the left how few lines of code are necessary to create a model like this. Now, you wouldn't even need to worry about any of these actual lines of code. I'm trying to convince you that the program is easy to use, and this version that I've created here uses parameters, variables in line 7 through line 13 here that set everything here. You don't have to change or do any work with any of these other lines of code here. Now, my program that I use for screen capture here isn't doing a very good job of capturing the cursor. So I'm going to have to try and describe what I'm doing on the screen here, and hopefully you can follow me that way. Over here at the left, as I said, lines 7 through 13 control what this model looks like. I'm going to try and step through each one of those to show you the impact of those variables. But presumably this hole here is for your boom. This large hole, as you see, you can't follow the cursor. This hole that's looks blue right now is the hole for the element. And for a parasitic element, the element would go all the way through the bracket. But for a driven element, you would have a split dipole driven element, and you can use this viewport here in front. It looks kind of greenish and then changes to blue as I pivot the model, and that viewport looks through into the hole for the element, and you can then slide your half of your driven element in from the left, the other half from the right, and use this viewport to center them up, get the proper spacing you want, and the hole on the left, lower left, and the lower right could be used with a small sheet metal screw or something like that to fix the element in place. Probably could even be used for making electrical contact to the element for connecting the feed line there. And of course the hole that you see up here at the top would be used for a small screw or a drop of glue or something like that to fix the bracket to the boom where you want it. Now, I said this was all parametric. If we go over here to line 7, and if you can watch me change that dimension from 30 millimeters to 50 millimeters, then when I hit F5, which is the re-render key, now I've made the hole for the boom larger. But everything else has stayed the same. The thickness around the boom, the thickness around the element, the material thickness I'm talking about, they all stay the same. I'm going to change that back to 30. But now I'm going to change over here in line 8, I'm going to change the boom diameter to 20. I'll hit F5, the element diameter to 20. I'm going to hit F5, and now I've made the boom hole smaller, but the element hole larger. Now, presumably you would measure your material pretty accurately, caliper or something like that, but you wouldn't want to use that exact dimension in these variables here. Or you would for the BD and ED, but for the model you want a little bit of extra slop. And I use the S parameter here in line 9, which I currently have set at 0.2 of a millimeter, to provide a little bit extra diameter for the boom hole and the element hole to provide the margin you need to slide the boom and the element through this bracket. I found that 0.2 of a millimeter works pretty well. Your mileage may vary. Now, if you wanted to change the thickness of the material itself around the element or around the boom, you would do that with line 10 here, the T parameter. And let's change that from 5 to 15. We'll hit F5 again. Now I've made everything bulkier. And we've changed the material thickness around the element and around the boom. The hole size, if you wanted to use a different size hole, can be changed with this H parameter at line 12. And I'll change that from 3 to 7, hit F5, and now we've got larger holes. Now, on the thicknesses, I'm going to measure this mention this just for information. I've got a radius set for the model to take away the sharp edges, but the way that OpenSCAD creates that rounded edge, it actually adds it to the base model. So in this case, we've got the thickness set at 15 millimeters and the radius set at 2 millimeters, which means that all of these thicknesses, the ones around the hole or the boom hole and the ones around the element hole, they're actually 17 millimeters in this case. If I change the thickness back to 5, hit F5, now instead of 5 millimeters around the holes, I've got 7 millimeters. Now, if you were going to use this configuration for a larger antenna, like an HF antenna, you'd probably want, first of all, thicker material. So let's change that from 5 to 10 over here in the at line 10. I'll hit F5. I've made that thicker now. But with in fact, let's change the element diameter to an even 25.4 millimeters, which is 1 inch. So let's say we had 1 inch diameter elements. They're probably going to be long enough and heavy enough that they would put a lot of stress, if this was the driven element where it's split, it would put a lot of stress at the point, imagine between the open hole here and the viewport. That layer adhesion there is fairly weak on a 3D printed object. So you'd probably want a reasonably thick material, and you'd probably want the width of this bracket to be wider so that you somewhat compensate for the heavy leverage of the element. And I added a variable at line 13 over here to the left. I call it X. Right now it's set at 0. But if I were to, for example, change that to 30, hit F5, now I've got a larger bracket, giving supposedly more support. I have no idea what the limiting case is for an HF antenna. I originally created this model for VHF and UHF antennas, but if somebody wants to give it a try for an HF antenna, I would suggest you do some playing around to get the support better for it. Okay, I made a similar file for a square boom, and I'm going to show that here. this is the exact same set of code, except it's creating a square hole instead of a round hole. You can change the variables for this model just exactly as you can for the round boom. And I'm going to make the OpenSCAD files available free on a website called Printables. It's printables.com. It's sponsored by Prusa, that company that makes my 3D printer. And those files will be freely and easily downloaded. Now, they will be an OpenSCAD file, just like you see over here at the left. Once you load up OpenSCAD with this file, I'm going to jump back to the round boom one. And I'm going to change those dimensions back because these look ugly. Okay. Once you have a model that you're satisfied with, we need to render it. And we do that down here at the same row of icons at the bottom. But we're going to click on the second one from the left to render the model. And you can see at the very bottom the green progress bar as the computer renders the configuration. And when it does that, all my colors go away and I get a default yellow color for the object. Now, this is a rendered OpenSCAD file, but it's still an OpenSCAD model. To change this to something that the 3D printer can use, we go up to the very upper left, and I know you can't follow the cursor, but go up and look where I'm clicking on File, and then I come down to Export as STL. And I click on that, and then that gives you the opportunity to save the configuration, save the model as an STL format file. And that's what you would do. Well, I've already got it, so I don't need to save it. And then you would use the slicer. If you have a 3D printer, you know what a slicer is, slicer application. The slicer application will take the STL file and convert it to G-code so that the 3D printer knows what it should be doing. So that sounds a little bit more complex than it is. It's just a sequence of events. If you are able to use the OpenSCAD program as I've shown here, I'm pretty sure you can follow that through, get an STL file that either you can convert to something that would operate on a 3D printer, or find a friend or somebody that can do the 3D printing for you. Okay, I made some models. I actually made some physical samples. Let's see what those look like. So here are some examples. This is a small one that might be suitable for a small antenna, like a 70 centimeter yagi or something like that. I have these 3/8 inch fiberglass rods. These are actually, they come 4 feet long. They're actually electric fence posts. There's clips that attach to these for holding the wires. But these things are very inexpensive, about $2.19 for this one. And I designed this particular bracket so that this would fit on here. And then some number 10 gauge wire fits in here. And you could make a very inexpensive 70 centimeter yagi out of this. At least if I get the wires straight. So here's another example. This one I made before I did the viewport. You can see
This one has the viewport. This one does not. This was an earlier version. But this would be for a round boom. And I sized this one for 1-inch PVC tubing. Goes on like that. And then the holes, these holes were sized for 1/2-inch aluminum tubing. Of course, this can slide along the boom, and these can be positioned this way. These holes can be used either to fix the element in the bracket by maybe putting a screw in there or a drop of super glue or something like that. But they could also be used, I believe, haven't tried it, for a driven element, provided you got the slot, viewport, so that you can properly line this up. I don't know if you can see that, like that. It allows you to get the spacing right. And then you could put screws in here that then attach to the feed line, as well as holding these in place and making contact to it. And this particular one I designed for a square tube that I had on hand, so this would work for a square boom. And as you may remember from the previous portion of the video, these can be sized to just about anything you want. You can change the boom configuration, whether it's round or square, the size of the elements, and in this case, whether it works for a driven element or parasitic element.
I hope you found some portion of that useful. I strongly encourage you to give it a try. As I said, OpenSCAD is an easy application to use. You can get the files from the printables.com website. We'll upload those as soon as I get the chance here. Thank you very much, and see you next time. Bye.